This is the last lecture for the unit, so that means that your test is coming up. Let's note the learning targets. The purple ones are the ones that we have learned recently. We've been talking about enzymes. And you guys did a poster. That poster is that lock and key model that the substrate has a certain shape and then it fits on to the enzyme and the active site that has a certain shape. Kind of like a lock and a key. A key has a certain shape and it fits to a certain lock. You should be able to tell me about what are the substrates, what would be the product, what's considered the enzyme. We then talked that enzymes can be shut down, and they can either be shut down through competitive or non-competitive inhibition. And when we're shutting down enzymes in a pathway, and it's the product of that pathway which will feed back to the beginning and shut down an enzyme that's used at the beginning of the process, then that's called negative feedback. And then we also talked about how enzymes have ideal pHs and ideal temperatures. You get too far from that, and the bonds in that enzyme and the protein are going to break, and then it's not going to work. It's going to become denatured. We're going to focus on now the last three here. We're going to look at what we could do to change reaction rate. There's four things that we can manipulate that we're going to focus on. We can change temperature, that's going to affect reaction rate, pH, substrate concentration, and then also enzyme concentration. Since we're talking about reaction rate, you're going to be calculating rate. Now, many of you didn't do very well on the first unit. So we're going to review how to calculate rate and make sure that you understand that if I say average rate, it's the exact same thing as just saying calculate rate. Then, last thing is you need to be able to draw these graphs that we're going to see today for the different factors like temperature and pH and substrate that can affect reaction rate. We've already said that temperature can affect reaction rate. And if temperature is varied and we have a reaction rate or a reaction taking place, we're always going to see that as you increase temperature, temperature goes up, but then when you get to a certain temperature, you see reaction rate goes down. So we're going to have reaction rate on this side, and then we're going to have temperature down here. Let's talk about why. You're going to be shown a simulation, and it shows you that molecules are moving, and in colder temperatures, they're moving very slow. As you warm them up, they'll move faster, and then they're going to collide more. And it's important that the substrate collides with the enzyme so that it can get in that active site and be turned into the product. So to understand the shape of this graph, you first have to understand that enzymes must collide with their substrates. And as you increase temperature, there's going to be more motion and more collisions. And so you're going to get more product formed as you warm up this beaker or this reaction. That's what we're seeing kind of here on this part of the graph. Come from here to here. You can see that this red line is going up. This is what I would deem as like part A here. Part A in the graph is showing you that temperature, so this is temperature down here, we're increasing it. Temperature is increasing as we go this way. So temperature is increasing. So there is more collisions, more reactions, and so as you go to warmer and warmer temperatures, the reaction rate goes up. At a low temperature, so let's put kind of a low temperature here, then we have a pretty low rate. But as we increase the temperature, so let's go right here, we can now see we have a higher rate. Now, part B is around, I would say part B kind of happens right here. So this is what I'm referring to as part B, which is right here. Part B of the graph. What is happening is we're seeing our red line has reached its max, but it's starting to come down. The reason why this is happening, it's not because the molecules are slowing down, it's because those enzymes are starting to become denatured. They have gotten too hot. This was the optimal temperature. So let's say For you, it's about 98 degrees. So your enzymes work best at about 98 degrees. But now we're up to, I'm just going to say 102. Actually, no, it's higher than that, 107 degrees. So therefore, your proteins are starting to lose their shape and they're starting to become denatured, and they can't assist in the reaction. So you can see the reaction rate drops. And if you continue to heat up those enzymes even more, you can see that rate drops because now they're getting just more and more and more out of shape. So there's no chance of them binding to the substrates. And eventually you can destroy all the enzymes at a high enough temperature and you're not going to have any reaction taking place. Let's take a look at how pH can affect temperature. And you're going to see the exact same thing. You're going to see a line go up and go down. Just like there's an optimal temperature for enzymes, there's going to be optimal pHs. Now, each enzyme is different. Each enzyme has an ideal pH. If you know about the pH scale, it goes from like 0 to 14, and 7 is neutral. So students always like to say the ideal pH is 7, but that's not exactly true. If we take a look at your stomach has a pH of about 2. And you produce an enzyme, here's the enzyme right here, it's called pepsin. And the ideal for pepsin is about 2. So I'm going to put pepsin, the ideal is 2. And you can see that it's making a lot of reactions take place at that pH. We have a very high reaction rate. Now, once pepsin moves from your stomach into your intestines are about right here. Here's your intestines. They have a pH closer to 8 or 9. Well, you can see what happens to pepsin activity. It stops working because you're too far from its ideal pH. Its ideal pH was around 2. If you get an enzyme too far from the ideal pH, they'll change their shape. They will denature. Therefore, the active site is a different shape and the substrate can't bind, so you won't be able to get a product. Next, let's take a look at these pictures, and we're going to look at changing substrate concentration. Changing the substrate concentration can speed up or slow down the reaction rate. Let's analyze this diagram right here. So we have substrate concentration. So if I'm right here, that means we got a low amount of substrate. So let's indicate low substrate. And the substrate's the circle. So you can see we don't have very many, but we do have 3 enzymes. And at a low substrate, we have a low rate. Well, let's look at why. Eventually, I mean, we've got these 3 enzymes. They're going to grab onto these 5 substrates, and then the reaction is done. I mean, that's going to be it. It's going to take a little bit, too, for them to get there because they're so spread out. Remember, they must collide in order to get a product. And since they're really spread out, it's going to take a little bit for a substrate to collide with that enzyme. So part A of the graph, we have less substrates to collide with the enzyme. There's going to be less collision, so reaction rate is going to be low. Now let's add a little more. Let's put kind of a medium amount here of substrate, and we can see that we now have a higher reaction rate. Well, they're more crowded. So there's going to be way more collisions because there's just more substrates to collide with those 3 enzymes. So an increase in substrate concentration allows for a greater reaction rate because there's going to be more collisions with the enzyme to make the product. Now let's take a look at this last line, because here we can see we have a very high substrate concentration. And even if I go from this high level to even more, you can see I don't even speed it up. My reaction rate is going to stay whatever this number is right here. Let's talk about why. Imagine if you were an enzyme and your job was to rip paper in 2, and that paper is the substrate. If I say rip paper one at a time as fast as you can and go, so let's say you get up to your maximum speed, your maximum rate right here. Now, if I just put more paper on your desk, can you go any faster? No, you've reached your maximum speed. your maximum rate. And that's what's happening right here. So more substrate won't increase rate past a certain concentration. If you go from this concentration to this concentration, yeah, it'll affect rate. It makes it go up a little bit more. But if you go from this concentration to this concentration, no. Rate is the exact same. So again, adding more paper when you have hit your top speed is not going to make you go faster. Same thing with a car. So imagine like the gasoline is like the substrate, and your car can only go so fast. Now, I'm not encouraging to do this, but let's say you have your car going as fast as it possibly can. Would adding more gas to your gas tank make you go past the maximum rate? No. The parts can only work so fast, and enzymes can only work so fast. And then the last thing we're going to look at here is how changing enzyme concentration can affect rate. You can see right here we have one enzyme. So we have one enzyme to collide with all of these substrates. It's going to take a while, and it can only collide so fast. So when we have low enzyme concentration, we're going to have a low rate, low reaction rate. We're not going to get a lot of product in a period of time. In this situation, we can see we have less enzymes. We have a low concentration to collide with those substrates, so our reaction rate is going to be low. Let's take a look at the next one. So now we have kind of this medium enzyme concentration. Now we've got more. So here we got 2. We still keep the substrate concentration the same, but now we just have another enzyme to assist in making the product. So you can see reaction rate would go up. And even if we add even more, so even more, notice there's no leveling off. If there's an unlimited supply of substrate and you keep adding enzymes, more and more enzymes, then you're just going to have a reaction rate that goes higher and higher and higher. There's no leveling off there. It's kind of like if I have an unlimited supply of paper and I have one person tearing it, we're going to have a rate like this. And then I add 5 people to tear. Then our production is going to be like this. And then let's say I add 100 people to tear, 100 enzymes to tear. It's going to be even crazy. I can't snap my fingers that fast. So you're just going to continuously increase reaction rate if you increase the enzyme concentration. Now on the next page, we're going to review rate again, and we're going to relate it to reactions. I can measure different parts of a reaction. Like, let's think about this. I can measure the rate at which you're baking cookies. I can either measure like the disappearance of the sugar over time and use that to figure out what is your rate of cookie baking, or I can count your number of cookies, the product, and I can then determine how fast you're able to produce cookies in a period of time. So reaction rate can be determined by either measuring the drop in the reactants, the change in reactants over time. Remember, we're always going to be looking at rate over time in this class. Or I can look at the formation of the product over time. Now let's think about this. Here's a reaction. So we have 2 reactants. We have our arrow. So these are the products over here on this side. And again, these are the reactants. If this reaction is taking place, then we're going to be decreasing the reactants. Reactants are going to decrease over time. They're going to be changed into the product. So it's kind of like this. If you're baking cookies, sugar is like what's needed. It's like a reactant. And your sugar levels are going to go down as you make more and more cookies. Products will be formed. They will increase. Again, think of those cookies that you're making. As you're baking them, like, you're going to just get more and more and more and more cookies. So the number of products is going to increase as a process is occurring. Let's take a look at these 2 graphs and see if you can figure out what the experimenter is measuring so that we can calculate rate. Here we have time, and we can see we had a high level of something, but it's dropping. So are we measuring the reactants being used or the products being produced? Well, hopefully this is easy, is reactants are going to go down in number as they're being used up. So we are measuring the change in reactants. So this is the change in reactants over the change in time. Over here, we can see that we're starting to make something, and it's going up and up and up and up. As a matter of fact, you can also probably see, hey, we're measuring CO2, and CO2 is a product. That's right, product. So if I can measure the increase in CO2 levels, I'm measuring the change in CO2, which is a product, over my change in time. Okay, so that's what we're monitoring in this experiment. Let's practice calculating rate now. A says calculate the average reaction rate. Don't do anything with a bunch of numbers and adding and dividing, all that stuff. As a matter of fact, you can mark through that and read it just the exact same way, and you're going to do this problem the same way. Calculate the reaction rate for the duration of the experiment. That means the whole thing. So let's put time on the bottom. That's the easiest. So we're going to go from the start at time 0 seconds. Let's go up. It was 2.5 M. That'd be moles per liter there, okay? Now let's go to the end. Okay, let's say that's all the way at the end there. Let's go 200 seconds. And then what coincides with that? Well, it's not a 0. Let's call that 0.1. We need to be precise. 0.1 M. We subtract those two numbers. So we're going to have 2.4 M. Then you're going to divide by negative 200 seconds. And that equals 0.012. Our units are M over S. So moles per liter over seconds. Now, don't forget that negative. It's important. We're going to put that negative in there because when you divide a positive by a negative, there's going to be a negative number. And that negative just simply means that something is decreasing. And as you can tell, it's the product. It's decreasing, so it's going to have a negative number because that slope is negative. Let's go on to the next one. It says calculate the initial rate of the reaction from 0 to 25 seconds. I could say calculate the average initial rate of the reaction, and you're not going to do this any differently. Again, let's put our time on the bottom. We have 0 seconds, and then we're going to go to 25 seconds. Put that minus there. At 0, we were at 2.5 M, moles per liter. And then at 25 seconds, oh, isn't that nice? They put it right on line for us. We were at 1.5 M. So then we do the math. So it's going to be 1 M divided by negative 25 seconds. And that's going to be negative 4. Actually, my decimal's off. 0.04. Let's try that again. Negative 0.04 moles per second. Last problem. You can stop if you want and try it on your own and then check yourself if you want. Calculate the average reaction rate from 1.5 minutes to 4. Again, who cares that I'm saying average there? Just ignore it. And let's deal with time on the bottom. 1.5 minutes to 4 minutes. Put the subtraction sign. At 1.5 minutes, let's go read it. We're at 30 milliliters. And then at 4 minutes, we were at 50 milliliters of CO2. Do your math there. We have negative 20 milliliters divided by negative 2.5. That's going to give us 8 milliliters per minute. Notice it's a plus because a negative divided by a negative, that means we got a positive here, positive 8. And positive means we have a positive slope, so you can see it's going up. So now we're done with notes. So you know a test is coming up, so be watching for that date.